All right, we're going to be starting relative motion analysis, but before I get started with that, just summarize where we've been, where we're going. First off, we're obviously in our kinematics of rigid body chapter. The first thing after introduction, we went into absolute motion analysis. Then we've just finished doing instant centers, and so now we're going to be going into what's called relative motion analysis and then into Coriolis acceleration. Now, in terms of this chapter, the focus of the chapter, in my mind, which will dictate how exams are done, is on relative motion analysis and Coriolis acceleration. So in your next midterm, you will have a problem in relative motion analysis, and there will also be a problem involving Coriolis acceleration. Going backwards with respect to instant centers, there may be a component of a problem on an exam where an instant center would be a useful way of getting information and moving ahead in the problem. But beyond pulleys, we will not be doing a lot with absolute motion analysis. So, what is relative motion analysis? It's really common sense. So basically, relative motion analysis says start from points where you know the motion, and then using relative velocity and relative acceleration, move from what you know to the points you don't know, and make them into points you know, and then just keep walking through. So we're going to do that with this problem here. So what I have is here's an input crank. So the understanding is there's a motor that's driving this input crank, the crank, and that's 2 radians per second, and it's currently speeding up at 1 radian per second squared. Now you notice I have a 2, a 3, and a 4 here. This is called a 4-bar mechanism. So where does that name come from? Well, if you look at the ground, so what I have here, here's the crank, here's the coupler, here's the follower, and then it connects to ground again. So the idea is as this spins around and around and around, all of these things just are swiveling and doing what they do. The ground connection is considered the 4th bar. So this bar, that bar, and here's the 4th bar. When you get to your next course with kinematics and mechanism design, you'll see these all over the place. These are used extensively. Historically, they were used actually in movie projectors. Something like a 4-bar mechanism would be used, and on this piece, the coupler, they would actually extend the coupler. So picture, as we've sometimes said, taking the bar and putting a piece of sheet metal on it. And what they would do is they would basically grow this piece to create this point here, point C. And actually what would happen is point C would go and it would advance the film. So as this thing rotated around, this piece would go in, grab the film, and move it ahead by 1 frame. So these mechanisms have been used to accomplish many, many things through the years. So it's called a 4-bar. You'll notice the crank is labeled as 2, so this is considered the second link. The first link is always ground. Second link, the input, and then you just go by connection. 3, the coupler, 4, the follower. So we're going to analyze this thing. So here's our input. We know what it's doing. And now here's where it connects to ground again. We also know the motion here at this pin, velocity, acceleration, 0. So what we want to do is figure out what's basically going on at A, B, and C. We could figure out other points, but those are the logical ones, and it's sufficient for what we're doing. So I want to use relative motion analysis and figure out velocity at A, B, and C. Omega 3 and 4, because omega 2, this link 2, I know it's angular velocity and angular acceleration, so I want to get angular velocity and angular accelerations for links 3 and 4. And likewise, I want to get acceleration for A, B, and C. And at that point, we'll pretty much know everything about this mechanism. So you start with velocity, and we'll just show this amount here. So you go from what you know to what you don't know or what you want to determine. So velocity here, 0. This is where the crank is pinned to ground. And we know omega, so we're going to go from 0 to a. So start from v0, and we can just note that's 0. Plus, now to go from here to here, this is simply omega 2 cross r from O to a. We know what those are, and we'll simply stick them in. Okay, so you have z cross x, that gives would give y, except x is 0, so there's no y component. Z cross y gives a minus x, so we have minus 2x meters per second. Okay, so once we're here, the idea is let's go to b. That makes sense. And we'll note we can do that two ways. We can go from a to b, and we can go from q to b. And we're going to need to do that because we're going to have two equations and two unknowns. And so this will help us with one, and that'll give us the other. So given b, we want to get b, given a, velocity a plus velocity of b relative to a. Okay, a is at minus 2x plus omega 3, so this will be whatever the angular velocity is of this. You'll notice I'll just write it as a positive variable. So the idea is I'm assuming this is going counterclockwise. Now if you let this thing rotate, you'll notice this is going to go like that. It's going to be rotating clockwise, so I'll get a negative sign for this. That's fine. Anything you don't know, I always take it in a positive vector sense and let the signs tell me different. Okay, so omega 3, assuming it's counterclockwise, will get corrected. Then we have here, to go b to a, we need to go minus x plus 2y to get to b. And so we have one equation. Now we're going to do it from q. Obviously q, velocity is 0. And then we're going to go b relative to q. All right. So that's 0. So to go the rest of the way, is omega 4 cross r from q to b. All right. So that'll be omega 4z cross, to go from here to here, it's just 2x. So you just look at your coordinate system and just follow it for where it tells you to go. So that says that VB would be 2 omega 4. If this were to go counterclockwise, B is obviously initially going up. So that makes sense. Well, given these two equations, I can equate them in the x and the y. So that's the next step. So if I equate the x's, I have minus 2 and a minus 2 omega 3 must equal, this has a 0x component. So minus 2 omega 3 equals 0. Bam, solve for omega 3. And we got it negative, so it's going clockwise. Perfect. Let's take that omega, stick it into the y equation. So up here I had minus omega 3, so that'll become plus 1 equals 2, from here, 2 omega 4. You get a quarter radian per second. And we can stick that back in, and we get VB is 1y meter per second going up. So that finishes off the velocity analysis. We've gotten all the parts, well, we've gotten A and B. We actually have to get C. So to get C, we'll just, let's see, will that fit in? Yeah, we can get it. So here's VC. So now that I know everything about how this thing rotates, I can actually compute this two ways. I only need one equation. I know VA, and I know all the parts of VC relative to A. VA was minus 2, plus, now it's omega 3, and then I have to go from A to C, so that's minus 1x. So I know all this. Here we have minus 2x plus minus z cross minus x, and that gives us VC. Likewise, so at this point, up here we needed two equations, two unknowns to get where we needed to go. Now we have two equations, but one equation is sufficient. The other one gives you a check for algebra errors. And so when you have something wrong here, it's an indication of somewhere either here or back here you made a mistake. That's great. It's always nice to be able to check your work. If we look at VC, it's equal to VB. plus c relative to b. Just common sense. So it's start at b and then c relative to b. Well, b is just y up. Then you have cross omega 3. That'd be the angular velocity here. And c relative to b, or I could have written, I'll note, I don't even think when I do this, this is the same as that. So c relative to b is the same thing as saying b to c. All right, I will, without thinking for one reason or another, I'll flip between these nomenclatures. All right. So again, I know all of that. Stick it in. I get the same answer, so that checks our work. That's useful. All right, so now we got to do, we've knocked off up here, VA, VB, VC, omega 3, omega 4. Now we got to do the same thing for acceleration. All right. So we know all that stuff. So let's just start this way. So acceleration of A. It's the same idea. We're starting from what we know and is 0. And then we're going to go A relative to O. All right. So that would be the 0 plus. Now I have alpha of length 2 cross R from O to A minus omega 2 squared R from O to A. That'll take me up to there. All right. I don't know this. Or no, I do know. This is the input. So the alpha, 1 radian per second squared. So I can just stick all of these parts in here. So I had alpha was just z plus z to go from O to A is plus 1y minus omega was 2, so 2 squared. And then R from O to A is y. So bam, here's my acceleration for A. So now we go to do B. And it's going to be the same thing. To get to B, I'll go up here to get one equation, and I'll go from here over to B to get a second equation. So here we have acceleration of A is minus x minus 4y plus, and you're going to memorize this thing. Guaranteed, you're going to do this so much you'll do it in your sleep. So to go from here to here will be alpha 3, we assume it's positive, let the signs tell us if it's not, minus x plus 2y to go from A to B, minus omega squared, well that was minus 1, so we square that. And then here again we have from A to B. All right? That's just the same equation we have here. No problem. And we get, do the cross products, this is what comes out. I'll let you check that. Now, the problem is we have one equation and we have we need to be able to figure those things out. We don't have enough. We need to equate this to something to be able to solve for this stuff. So, bam, we're going to do it from Q. So, Q is 0 plus acceleration of B relative to Q will be 0 plus alpha 4. We don't know the angular acceleration here, so we'll assume it's positive, so that's alpha 4z. And then we go over 2x, alpha cross R, minus omega squared, is a half, R. So there's our 2x again. Multiply all that out, and we have this relationship. Well, if you look at that, we can now equate the x's and solve for alpha 3, and then we can equate the y's knowing alpha 3, and we can solve for alpha 4. And that's given right here. Now, we were asked to figure out the acceleration at B. Fairly easily done. Let's just bring these more side by side. And so here's the acceleration at B. We just take these terms, stick them up into there. So alpha was 4 is 25 on 8. So if we multiply by 2, we get minus 1 half x minus 25 over 4 and an ugly y, meters per second squared. At this point, all that's left is we just need to compute AC in terms of the requirements. So starting from A, which was minus x minus 4y, then we'll need to get C relative to A, and that's just always the same basic equation. So it's alpha 3 cross R from A to C minus omega 3 squared R from A to C. So all you ever have to do is just adjust the subscripts in this equation, and you're off to the races. So we have all these parts, we just stick them in, bam, there's AC, and we'll note we could have gone from B to C, and naturally, if you do all your math right, you get the same answer. So there's a check. We're going to do a bunch more of these problems. We'll see you again in a moment. Bye now.